Okay, hello everyone. Welcome to today's lecture. I have shared my screen. And hopefully, you can see my slides. So, last time we were talking about analog to digital conversion and how we can do that on AVR microcontroller. So, we had a look at just like basic things, like for example, what is resolution, what is step size, how to convert mathematically an input analog voltage into equivalent digital output, and like basic, what are the basic characteristics of analog to digital conversion, right? So today we'll continue our discussion. So we will talk basically about how we can program or how we can use the analog to digital conversion module in AVR microcontroller. Uh, and then in context of that, we will have a look at different registers like ADCH, ADCL low, ADCH high or ADCL low, ADMUX, and ADCSRA register, right? So this slide is basically same which we have covered in the last lecture. So as we have seen in last lecture at Mega 328P microcontroller, which is the microcontroller used in the Uno R3 board, it has an internal ADC component, which means basically you don't need to interface any external chip to do the analog to digital conversion. It is on chip, and it supports 6 or 8 analog input channels depending upon the type of package. So if it is a DIP package, which is like the one like in shape of rectangle. So that package has 6 input channels, but if it is a flat package is one which is smaller in size and which doesn't have, legs. It is like its pins are straight. You cannot, for example, plug it in on the breadboard, right? So that type of package, TQFP package, it offers 8 analog input channels, which basically mean, and by input pen channels mean that we can interface 8 different, or we can connect the 8 different analog inputs, right? 6 or 8, depending upon the type of the package. Also, for ADC on on this AVR microcontroller, we have 2 external sources of VREF. Remember what was VREF? VREF was like the upper limit of the range of the analog voltage, which we which we want our ADC to sense. So, for example, if VREF is 5, we are saying that our input analog voltage will be in the range of 0 to 5. If VREF is 3, we are saying our input analog voltage will be in the range of 0 to 3, right? So at Mega has it offers 2 external sources, like mean it gives you the option. So one one of those external VREF, it is connected with the power supply, which is 5 volt. But let's say if you don't want to use 5 volt, then there is another pin which you can use as a VREF. It is known as AREF. So you can connect other voltage source as an upper limit. For example, if you want to say I want my signal to be in the range of 0 to 3, but your VCCs or supply voltage is 5 volt, so then you can use the second external source of VREF, which is referred as AREF, analog reference voltage. Other than that, it also offers one internal VREF generator, which means that if you want to use the internal, just give me 1 minute, I will. Okay. So other than these 2 external sources, you also have an internal source available, which means that you don't need to make any interface or any connection. So it is on chip, and that is fixed to the 1.1 volt voltage, right? So you can select one of these three, 2 external sources and one internal source of reference voltage. And ADC on AVR microcontroller is 10-bit, which means that it generates 10-bit digital equivalent of your uh, input analog signal. Okay. Okay, memory addresses for registers related to analog to digital conversion. So there are, as I said, there are different registers. For example, ADC low and ADCH high, ADCSRA, which is like ADC status register A, control and status register A, ADCSRB, and ADMUX and DIDR0. So we will have a look at all of these registers. But in this slide, what we just want to highlight is that all of these registers, they have their memory addresses, but they don't have an address in IO space, which mean basically that since they don't have address in the IO space, you cannot use in or out instruction with these registers. So for example, if you want to write some value to, let's say, ADCL register, you cannot use the out instruction. Similarly, if you want to read value, let's say from ADCL register, you cannot use in instruction. Why? Because their addresses are not located in the IO address space. So that's why if you want to access them, like read or write them, you need to use LDS and STS instructions, right? Load from static memory and store to static memory. So uh, just to visualize what I said, if you, let me select the point. So just to visualize what I said, if we look at memory map of the memory map of the AVR microcontroller, so first 32 registers addresses are occupied by the 32 registers, and then we have IO address range, right, from 0020 to 0x005F, and then we have 160 extended IO registers, and then after that internal SRAM. So these registers, which are associated with ADC, their addresses are within this range, 0x0060 to 0x00FF. So since they are not in our range, so we cannot use in and out instructions with them, right? Okay, now let me go and release the poll one. Oh, no, I'm not creating breakout room. Yeah. Okay, go ahead and you have 2 minutes to complete our quiz. Please, guys, I want all of you to participate. There are 29 participants, excluding me, 28. But until now, only 10 people have answered the first question. Mhm. Okay, I'm ending the poll here. And let me just like give you the answers. So depending on the packaging, Atmega328 has 6 or 8 input channels for ADC, and Atmega328 has 10-bit ADC, right? And third question, Atmega328 has two external and one internal VREF sources, right? And ADC registers, they can be accessed using in or out. No, they cannot be. This so statement is false. Okay. So do we answer all of them or just the first one? Sorry, I am late to respond to it, but you are supposed to answer all of them. Okay. Okay, so now let's continue with the next slide. So remember, I said there are different registers associated with the ADC or analog to digital conversion. So two of those registers are ADCL and ADCH. Actually, these two registers are used together, like in the combined form, to store the result of the conversion. Remember that the ADC generates 10-bit result, and each register in our microcontroller is 8-bit. So that's why we use two different registers to hold the 10-bit result. So ADCL holds the lower 8-bit and ADCH holds the upper 8 bits. Sorry, not upper 8, upper 2 bits only, right? Because the result is 10-bit wide. So the 10-bit result, it can be either right or left adjusted. What does it mean? So here you have these two registers in graphical form, ADCL and ADCH. So actually, you have a bit which is named as AD left adjustment register. So this bit is actually in the control register, which we will see in a minute. So if you set the value of this bit equal to 0, so you are saying that the results are right adjusted, right? And the result will appear as shown in this figure from ADC 0 to ADC 9, and the upper 6 bit of ADCH, they will be unused, right? But if you set this bit ADLAR equal to 1, it's mean you are saying that make the result left adjusted, which mean that least significant 6 bit of ADCL, they will not be used, and the result will be held in the 2 bits of the ADCL and 8 bits of the ADCH register. Okay. Any questions? Okay. So with this, let me go to, yeah, you have 30 seconds to complete it. Let me give you 45 seconds. Okay. So the correct answer is like, if you set the ADLR bit, the result will be left adjusted, not right adjusted. 5 of the participants, they actually selected the wrong answer. See here, if you are setting this bit equal to 1, ADLAR bit equal to 1, the result is left adjusted, right? The right bit, the right side is empty, right? Right side of it is the lower 6 bits are empty. However, if you are setting it equal to 0, then result is right adjusted, and most significant 6 bit on the left side, like ADCH, highest most significant 6 bit of ADCH, they are empty. Okay, so the other register associated with AD operation is ADMUX register. So let's have a look at different bits of this register. So the first two bits, uh, uh, ref S0 and ref S1, these are used for selecting the reference selection bit. So basically, remember we said that there are three different reference voltages or inputs which we can use. Two are external and one is internal. So yes, there is option, but then we need to decide which one of them we want to use, and how we communicate our decision to the AVR microcontroller by setting these two bits, right? So uh, don't look at the table. Let's first look at the figure on the right. Ignore the table for time being. So this is like the internal circuitry. So this is your input pin. This is like this is a pin on your microcontroller. This is also a pin. So this is AVCC, which is connected with the power, which you need to externally connect with the power supply, and AREF, which you can select with any analog voltage, right? And this is internal. 1.1 volt, right? And here you have two control signals, and this is a mux, right? So if you select for example, if you are sending on this line, you are sending 0, then it's mean AVCC will be selected and it will be connected to the output. But if you are sending 1 here, then it's mean that this input will be selected and connected to the output. And then this second line, ref 0, it actually just controls this switch. This is nothing but a transistor which acts as a switch. So when you provide 1 as input at this one, so this switch is connected. So basically the two sides of the switch are connected together. But if you provide 0 as input, then this switch is open. So which basically mean like the two inputs are two sides of the switch are not connected, right? So for example, if let's say now I select, for example, if I select 0 and 0 here, let me change the color. So if I select 0, 0, so it's mean that this AVCC is connected from here, right? And uh, so yeah, so if I connect, if I select 0, so this AVC is connected on the output, and this switch is open here, right? If I'm selecting 0, so which mean that A ref will be provided as output as input reference voltage to the internal circuitry of the ADC, right? So similarly, for example, if I select 0 and 1, so which mean basically I'm saying here it is 0, but I'm replacing this one with 1. So what will happen that this will be selected here, and then this switch will be closed, and as a result AVCC will go out at the output. However, note that there is a hardwire, there is a connection between AREF and this output, right? So which means that if we want to use AVCC or internal 1.1 volt, we should not connect externally this to anything, right? Otherwise, for example, if you have connected it, let's say with 1.8 volt, and then you are here, you are saying here you are selecting, I want to use 1.1 volt. So what will happen is, again, let me use a different color because I have drawn so much. So what will happen that this will be selected here, right? But at the same time from here you are getting 1.8 volt. So when you have two different voltages, so it's mean at the output you will not get 1.1, right? Which is your desired. So that's why if you want to use either AVCC or internal 1.1 volt, you should not connect AREF with any external output. So you don't need to worry about that, at least in our course, because we are not going to use AREF for the time being, or at least in our upcoming lab. So okay, before going there, so this is actually the table which gives you the combination. So if you select 0, 0, it's mean you are saying 0, 0 in these two bits here. So you are saying, okay, I want to use AV ref pin. So whatever will be connected here, it will be used as a reference voltage. 0, 1. So it's mean that you are saying, okay, I want to use whatever is connected here, which is typically you connected with the power supply. So it will be used as reference voltage. 1, 0 is reserved, and 1, 1 is like you are saying, okay, I want to use the internal 1.1 volt as a reference voltage. Okay. And actually this is the same thing which I said earlier. So far, if you want to use AVCC or the internal 1.1 volt to make them usable, you must not connect a ref. There is a mistake, not ARFE, but AREF. AREF must not be connected externally because as it is shorted with switch output, right? Because the switch output is connected together with the AREF. Let me make this correction quickly, otherwise I will forget. Any questions? No? Okay. So we have seen what is the job of the first two bits of the ADMUX register. When I say first two bit from the most significant bit side, they are used to select the reference voltage, right? Source of the reference voltage. The ADLAR bit, so it is the left adjust bit for the ADC result, which we have seen in the previous slide, what is the job of this bit. So if you set equal to 0, the result will be right adjusted. If you set equal to 1, the result in the 10-bit result will be left adjusted. Okay. Uh, okay. Uh, so other than that, in the ADMUX register, we have 8 bits mux from like mux 0 to mux 4, which are used to make some selections. What kind of selections? To select the analog channel and gain selection bits. For time being, forget or ignore this part, gain selection bit. Let's just focus only on analog channel. Remember, we said that the ADC microcontroller, ADC on the Atmega328P microcontroller, it supports either 6 or 8 channels depending upon the package. But even if it is supporting, let's say, 6 channels, still we need to select like which one of them we want to be converted to the digital form. I don't know whether you remember it or not, but in last lecture we said, I remember, you can have multiple input channels, like let's say uh, C0 to, let's say, C8, C7, 8 input channels, and then you have 8-bit output, digital output, let's say. I'm just writing it, let's say, from D7 down to D0, right? But so which basically mean on left side you can interface, let's say, at max 8 different analog inputs, or let's say 8 different sensors, right? However, on at any given time, only the input from one channel can be converted into its digital form. All the 8 inputs cannot be converted into digital form at the same time. So you need to tell the microcontroller to that from which analog input in it should read the analog value. So for that, you need to write these bits of the ADMUX register, right? And that is known as, like, we are selecting the analog channel, right? Let me just simply discard uh, all this stuff. So here is the figure. So you have this ADC multiplexer selection. So actually it is like these bits, mux 0, mux 1, mux 2, mux 3, and they go to the mux decoder. I don't know whether you guys know how a mux works or how mux decoder works, but I'm not going to explain it here because this is not our course on digital design. So, or digital logic. So I mean, I'm just skipping this part because if I go into like how a mux works or how a mux decoder works, then it will take time. And by the way, that is not even the focus of our course, right? So, so uh, based on these, why can't I select the? Come on. So based on these 4 inputs, Mux decoder will generate an is control signal, and then based on that control signal, let's say if you have 8 channels, one of them will be selected. So and then it will be passed to your ADC logic to convert the signal in from analog shape to the digital form, right? So for example, in Atmega 328P, if you have DIP packaging, so there will be only 6 channels available, ADC 0 to ADC 5, and these are the values that you will need to write in these bits mux 0 to mux 4 bits of the ADMUX register. So all zeros, if you want to if you want to tell the microcontroller to read the analog value from this pin ADC 0, 0001 if you want to select ADC 1, and so on, 2, 3, 4, and 5, right? Okay, so what about this gain and selection? What about this gain selection bit, or what about gain for what is meaning of this gain for differential channels, or combination of analog inputs? So actually the thing is, like, here we are saying that you can select one of these, let's say, 8 different channels. or for example, if you have connected 8 different sensors, you can tell, okay, convert the analog value from sensor 1 into digital form, right? But there can be situations where you want to actually convert not the value of which is analog value generated by a sensor, but you want to, for example, let's say check the value of 2 different sensors, analog values generated by 2 different sensors, and then based on the difference between these two values, you want to convert that value and then take some action, right? So in that case, that is known as uh, uh, combination of analog inputs. That is what is meant by combination of analog inputs. So what you are doing is, like, for example, read 2 different analog inputs, take the difference, and then convert the difference into the digital form, right? And by gain for differential channels, it's mean that sometime it is possible that you are using sensors which generate the analog signals, like for example the voltage, but the voltage level is too small. For example, let's say instead of being volt, it is, let's say, millivolt or microvolt. So what you need to do is that before converting, you need to first amplify that voltage level, or you need to increase its voltage level. So which basically means you need to apply the gain on that voltage. So, but we are not going to cover that part in our course, so that's why I haven't included how to set these bits mux 0 to mux 4 when you want to use combination of analog inputs, or when you want to apply the gain for differential channels. But however, if you are like if you are interested, you can go and you can check and read the book, and there you can see how you can set these values bit 0 to bit mux to select the combination of analog inputs and to select the gain level. Any questions? Okay, if no questions, then let us go and have the poll 3. Okay, yeah, you have 90 seconds to do this. Okay, so I'm ending the poll now. What's happening? Why I can't even end it? Okay. Okay, so let's have a look that how what the value should be, right? So what uh, we wanted to use ADC3, right? Like we wanted to select this one as input. So if we look at the table, this is so here I'm starting 1 1 0 0 0, and we wanted to do the right adjustment, right? So this will also be 0, and we wanted to use internal reference voltage. So for that, you can go back, and so you need to set 1 1 1, right? So here you will have 1 1. So when you convert it into the hexadecimal form, you will see it is equal to C3, 0x C3. Okay, guys, let me stop. There is something wrong. Okay. Okay. Yeah. Now we can continue with, let me just erase all these annotations. Okay. So the other register which is associated with the analog to digital conversion is ADCSRA. Actually, it stands for analog to digital conversion control and status register A. So which basically mean there are two registers, register A and register B. So let's first have a look at the register A. So if we start looking from the most significant bit side, bit 7, so it is ADN, so which mean analog to digital conversion enable. So if bit 7, so if you want to use analog to digital conversion, you first need to set this bit set equal to 1. So which means you need to enable the ADC component of the microcontroller. So if you write 0, it's mean that your ADC will be not working, it will be disabled, right? The bit 6, so remember we said that the ADC, it takes input from the analog input. So but let's say analog input, when should, yes, the analog input or analog voltage is available on the input line, but when should our logic should start conversion, right? So for that, we need to first specify, for first we need to set this bit 6 equal to 1. So if this bit is equal to 1, only then your AD will start the conversion. And if you like write it back to 0, then conversion will stop. Okay. So you need to do, these are two different things. So for example, actually to perform the conversion, you first need to write 1 here, and you also, by writing only 1 will not start conversion automatically. After that, you need to write 1 here as well. Okay. Bit 5, ADC auto trigger enable. So what does it mean? So basically your let's say your input is 1 point, let's say 1 volt on this input, right? And you say, oh, okay, I want to convert it into the digital form. And then let's say it stays 1 for let me draw this signal, right? So let's say the input stays 1 for 2 seconds, right? So do you want to like how frequently you want the analog input to be converted into the output, right? One way is like you can say, okay, I will manually control it. Whenever I tell you, okay, start conversion, then read the input and convert it into the digital form. The other option is that you say, okay, I'm not going to manually tell you every time when I write 1 to the ADSC bit, then start the conversion. Actually, what you can do is, I'm telling you that, okay, you can read some sources or some events, and whenever that event happen, read the analog input signal and convert it into digital form. This is known as auto trigger. So you don't, in your code, you don't need to you don't need to repeatedly set this bit 0 to 1. Whenever you will say 0, the conversion will stop. When you say 1, this in this bit, so the conversion will start, right? So one option is you do it in your code, like every time before starting every conversion you write 1, and after ending every conversion you write 0. Then again, when you want to read the analog input, you again write 1, and then after conversion you again write you set it to 0, and so on. The other option is that you can specify a source or an event, and whenever that event happens, the microcontroller will automatically read the new value and convert it into the digital form, right? So here we are saying, like, do you want the auto trigger to be enabled or not, right? So if you say not, if you set equal to 0, so there will be no auto trigger, and you will be required to whenever you want to start the conversion, you will be required to write 1 in this bit, and whenever when you want to stop, you will be required to write 0. Okay, ADIF bit. So bit 4 ADC interrupt flag. Actually, this bit is set to 1. not by the programmer or not by you, but actually it will be set by the hardware. So it is an interrupt flag. It will indicate that, okay, now the ADC conversion is completed. So for example, here you write 1 and then you keep reading this bit. So when this bit become ones, it is telling you that, okay, conversion is completed, right? And which means that after that you need to again you can start the new conversion. Okay. ADIE enable. So it is bit 3 ADC interrupt enable. So basically, when a conversion is completed, right? So for example, you read the signal 1 volt signal from here. So and you convert it into 8-bit digital form. And how you know the conversion is completed? By reading this bit. When this bit is equal to 1, it means the conversion is completed. So once the conversion is completed, what to do? You need to do something with that 8-bit digital value which is placed in ADCL and ADCH, right? So what you need to do some kind of action, right? So there are two options, like who is going to take care of that data which is produced in ADCL and ADCH. One option is that you can say, okay, I will continuously monitor this flag, and when it comes 1, then I will go ahead and I will read the value from those registers and I will do whatever I want to do with those values, right? The other option is, so if you do that, it's mean what you are doing is like, if let's say if your program is like this, you are doing some program, or you're doing the initialization, and after that, once, and then you are saying, okay, start the conversion. I'd like, let me go back to OneNote to explain the things, because here it is just a bit difficult to write. Okay. So how we can visualize it? So for example, let's say this is your microcontroller, right? And, this is, let's say, ADC0, and you have selected in MUX register that you will read the value from this line, right? And then in your control register, you said AD enable equal to 1, and then you said AD start conversion equal to 1, right? So which mean that the voltage from this line, let's say the voltage is, I'm just making up some number, 2 volt, it will be read, and then it will be converted into the equivalent digital form, right? And now I don't know what is that digital form. I'm just writing some bits, right? Let's say it is equal to 0x02, right? So this will be placed in ADCH and ADCL, right? But how do you know that the conversion is completed? For that, you need to check the ADI interrupt flag, right? You will be continuously monitoring, reading it continuously. So if this flag is equal to set equal to 1, it's mean that conversion is completed. And now what you can do is that you can go ahead and read this value and maybe put in it somewhere. Let's say you can put it in combination of R16 and R17. You can do something, whatever you want to do with this data, right? So, but what does it mean? The problem is that if you do so, you will be continuously looping here. As long as your conversion is not completed, you will not be able to continue with your rest of the program, right? So, which means you are wasting the time here, right? The other option is that you can say, okay, I'm not going to wait. So just start the conversion. I'm not going to do this thing. I will not, this is known as polling. So I am not polling my interrupt flag. So and I'm enabling interrupts, which mean that whenever this conversion is completed, give me a signal, right? Just enable the interrupt. And then what you're doing, so actually what happens that when the interrupt arrives, so in the memory, there is a specific location, and in that specific location, you can write a code, put a code, which is known as interrupt service routine, right? So which is basically doing the same thing, whatever you was doing here manually, right? So you can put your code, your code here, same thing, which I don't know how to indicate it. You can say, okay, R17 down R16, put in them the value from ADCH and ADCL, right? But the good thing is that this time, but you have to first put the code in this in a particular location in memory, right? Which is known as the address of the interrupt service routine for the ADC, right? So if you have written your program here, after that you will do enable analog to digital conversion, start the conversion, and then you will continue with your rest of the program. Now, this time what will happen? You don't need to do the polling, which means you don't need to continuously monitor the interrupt flag. As soon as the conversion is completed, your microcontroller will automatically jump and start executing this code. And after executing, it will for example, let's say when the conversion completed, you were at your microcontroller was executing this instruction, let's say instruction X in your program, right? So after executing instruction X, it will go to it will find that, okay, interrupt has arrived, which means that the conversion is completed. So the control will go to this memory area where you have already saved the code to handle the result of the conversion. And that code will be executed. And after that, your control will come back to the next instruction after instruction X, let's say instruction Y, right? So now the good thing here is that you are not wasting time in continuously monitoring the ADIF flag, right? Whenever your result is conversion is completed, interrupt will arrive. Your microcontroller will automatically jump to the location where you have saved the ISR or interrupt service routine for the ADC. It will execute that code, and after executing, it will go back to the program, same point where it left. Okay. Any questions? Any questions? No? Okay. So yeah, so this is what we meant by, so but for that thing, so actually there are two different ways. There is a polling mode or an interrupt mode to handle the output generated by the ADC, right? So in polling mode, you don't need to enable interrupt. You can write here 0 if you want to use polling, right? But if you don't want to use polling, you don't want to like waste the time, then you need to enable this one, right? Not only enable this one, but also you need to put at a specific location in memory the program which will take care of the result generated by the ADC, right? So to enable ADC conversion, complete interrupt, right? And then the remaining last three bits, 0 to 1, they are like known as the prescalar bits. We will talk about them in the upcoming slide. Okay, so these bits actually let me explain in the next slide, not here. So any questions? Okay, if no questions, then let's go to the quiz 4. Okay, go ahead and you have 60 seconds to complete it. Oh, sorry. Yeah, okay, okay. You have 60 seconds to complete it. Yeah, go ahead. And you need to answer all the questions in here, not only first question. You have 3 different questions, so you need to answer all of them. I can give you 30 seconds more. Okay, I'm willing to increase it to 2 minutes, but I want you guys to participate. Please don't sit idle there. Participate in these quizzes. Okay. So ADC in Atmega 328P can be used in two modes, right? Which mode? One is your polling mode, the other one is interrupt mode, right? Question 2, polling mode of ADC operation wastes CPU time while interrupt mode does not. That is correct, true, right? Which bit of ADCSRA register must be set to 1 to enable interrupt mode of operation? Bit 3, bit 1, bit 3, bit 5. So it is bit 3 here. Okay. Okay. So we said like last three bits, 0, 1, and 2, they are used as prescaler select bits. So what is meant by prescaler? So actually the thing is this. Your microcontroller is operating on a clock frequency, right? So, but your ADC also needs the clock input. However, the issue is, the problem is that the frequency at which your ADC operates, it must be less than 200 kilohertz. Like for example, if your microcontroller is let's say running at 2 megahertz, then you cannot supply directly that 2 megahertz clock frequency to the ADC. Why? Because ADC can run on frequencies only which are lower than 200 kilohertz, lower than or equal to 200 kilohertz, right? So that's why what they provide you, or what there is an option that you can actually divide the frequency of the microcontroller by a denominator, and then you can provide the resultant frequency as input to the ADC, right? So here here the one input is like whatever clock frequency you have for the microcontroller, you divide it by 2 and make it an input of the mux. So for example, let's say if it is 2 megahertz, so this input will be equal to 1 megahertz, because if the clock frequency of the microcontroller 2 megahertz divided by 2 becomes 1 megahertz. And here it is by 4, so it's mean that it will be 500 kilohertz. And this is divided by 8, so 2 megahertz divided by 8, so 500, and then 250 kilohertz, and so on, right? So you can do the math, right? So these are different inputs, so these are already available there, right? 7-bit ADC prescaler, right? So then you can select one of them. So these are select lines. So depending upon like the values which you are providing here, one of these not eight inputs, 7 inputs will be selected and connected to the output, right? So for example, if you are saying all these three bits are 0, so then this input will be connected and it will to the output. If you are saying that the input is 1 in binary for these three select lines, then the second input will be connected to the output, and so on, right? So here is the table. Sorry, my mistake. So if it all 0, it is reserved, it is not used. But it is, if it is 0, 0, 1, then clock by 2 will be connected to the output. If it is 0, 1, 0, then clock divided by 4 will be connected to the output, and so on. So if it is all ones, then clock divided by 128 will be connected. So now which one of them you need to connect? It depends upon what is your the clock frequency for the microcontroller, right? So let's say if clock frequency for the microcontroller is 2 megahertz, and we said that this output should be, whichever we are selecting, should be less than or equal to 200 kilohertz, right? So if you, let's say, divide 2 megahertz by 2, it will be 1 megahertz. By 4, it will be 500 kilohertz. By 8, it will be 250 kilohertz. And by 16, it will be 125, right? So this is your first value which is eligible to be for the selection, right? Because we said that it should be less than, output should be less than or equal to 200 kilohertz. So like you can select this one, right? or any one which is lower than 120, like for example, clock divided by 32, clock divided by 64, clock divided by 128. However, if you are selecting smaller clock values, let's say if I divide 125 further by 2, so what it will become, it will be like 50, 60, and I don't know, maybe 63 or something, right? So the clock frequency starts reducing. So lower the clock frequency that you feed to the ADC, then ADC will operate at lower speed. So what we want is, like, we want the highest value which is less than or equal to 200. So in our case, in this particular example, the highest value which is less than or equal to 200 is 125. So we can use this one, right? Any questions? Okay, if no questions, then let's go to our next poll. Okay, you have 30 seconds to complete. Okay, I can increase the time to 1 minute. So you have 30 more seconds. Okay, so the correct value will be 0x6, right? You can actually see it from the table, right? This one. Okay, let's go to the next quiz then. Okay, if you want, I can go back to the previous slides. Yeah, you can see from here. Okay, I can give 15 extra seconds. Okay, let's stop here. So what should be the value, right? So we want to enable the a, analog to digital conversion, but we don't want to start the conversion at this time point. We don't want to enable the auto trigger. We will keep it 0 because this is readable flag. We are not setting it to, we cannot write it. And then we are not enabling interrupt. So this will be 0. And then we want to select clock divided by 128. So all these 3 bits will be 1. So when you convert it into the decimal hexadecimal form, so it will be 0x87. Okay. Okay. The another register that is associated with ADC operation is, actually it is not directly related with the ADC operation, but we need it for, like, meaningful use of the pins. So this is known as digital input disable register. Remember, let me go back to our lecture one, because I want to show you something. So, here, uh, where is the, where are the pins? Yeah, here. So for example, see that our these pins, PC0, pin 23, 24, 25. So they are all of the pins are actually multi-purpose, right? But to pin 23, 24, 25 up to 28, they are used as PC0, PC1, PC2, PC3, PC4, PC5 up to ADC, and they are also used at ADC0, ADC1, ADC2 up to ADC5, or for some other purposes like interrupt 8, interrupt 9, 10, 11, and so on, right? So they are multi-purpose. So what we want to do is that we want to, when we are not using them as digital input pins, so we need to disable their input buffers. Why? Because those buffers, if they are enabled, they use the power. So if we don't want to waste the power, we can simply disable them, right? Even if you don't disable, still it will be fine. Your program will work. You can still use the ADC, but it's better to disable those input buffers because we are not using these pins as digital input pins, right? So that's why, and in order to do that, what we need to use is this DIDR0 register, digital input disable register, right? So when you set value of 1 at a bit, the digital input buffers are disabled to save the power. So for example, for port C. So, but you know that in the uh, in the variant which we are using, there we have only 6 input channels from like 0 to 5. That's why when you write 1, so the input buffer for the input pins like PC0, PC1, PC2 up to PC5s, all of them will be disabled, and you will have some power saving. Bit 7 and 6, they are not used in the sense that our ADC is already 6 channel ADC. And other register which is associated with ADC is uh, AD control and status register B, right? So let's have a look at its different bits. So bit 7, it is not used. Bit 7, it is ACME. What is ACME? It is analog comparator multiplexer enabled bit. Actually, this bit is not related with the operation of the ADC. So if you can simply ignore it in the context of AD operation. It is not relate. It doesn't contribute anything to the AD operation or analog to digital conversion, but it has some meaning when you are doing analog comparison between two different analog inputs, right? So actually, if you look at if you go back to the lecture one and you look at the pin layout of the microcontroller, there are two pins which are labeled as AIN0 and AIN1. Actually, you can give two analog signals, and then you can ask your microcontroller to compare them, and then based on that comparison you can do some action, right? So if you want to do that, you first need to enable the analog comparator, right? And how you enable it? By writing 1 in this bit. However, this bit is not related again with the analog to digital conversion. Then we are left with bit 5, 4, and 3, which are not used. And the last three bits, bit 0, 1, and 2, they are actually used to select the source of the auto trigger. Remember, when we were talking about ADCSRA register, we said we can select when the new conversion should start. Either we can do it manually by setting the start bit equal to 1, and then setting it to 0 when we want conversion to stop when the conversion is completed. Or the other is that we can select an event, and then we say whenever the event happen, the next conversion should start automatically, right? But what is that event, and what is the source of that auto conversion, right? So we can specify that source by setting these three value of these three bits, right? So, and here is the table, like when you are setting all three bits equal to 0, so it says free running mode, which basically means that continuous conversion will happen after the first one. So once the first analog signal is converted into into 10-bit and digital value, microcontroller will go ahead and read again the input and convert it, irrespective of whether the input has changed in its value or not, right? Uh, and then there are some other events. For example, you can say, okay, based on the timer, if the timer overflows, then start the conversion. Or for example, you can say, okay, compare the analog input, and if the start conversion when the comparator output changes, so which means that two input analog signals, they are not same, and so on and so forth. So I just wanted to include it here for the purpose of completion. But in our lab, we are basically going to use the polling mode, or we are not going to use the auto trigger source, right? We will every time we will say, okay, now the completion is conversion is completed. We will, after that we will read the value and then start the conversion again. Any questions? Okay, uh, so we have seen all the registers which are related with the ADC operation, right? But now is the time to put all that information together to write a meaningful program, so that we can read an analog value and convert it into digital form and then take some action based on that. So what are the steps for writing such a program? First, you need to do the initialization. So if by the the first thing in the initialization you need to do is that you need to disable you need to disable the input buffers for your analog input pins, right? So you can do that by writing one at bit 0 to bit 5 of DIDR0 register, right? Second, you need to set the values in the ADMUX. So what values you need to set? So you first need to select the reference voltage. And for example, you can write 0, 1 to select VCC as reference voltage. It depends upon what you want to select as a reference voltage, right? For example, if you want to select the internal voltage as the reference, then you will write 1 is in these two bits. Then you need to also specify whether you want your result to be right adjusted or left adjusted. For example, if you want to be right adjusted, then you will write 0 into this bit of the ADMUX register. Then mux 0 to mux 3 values bits, you will write these values to select the ADC. For example, if you want to select the input as ADC 0 as input, then you will write all zeros in these bits. Okay, ADCSRA register. Uh, Actually, I think there is a mistake. Here it should be right, because there are 4 bits. And okay. Uh, Other than after setting the ADMUX register, you also need to set ADCSRA register. So for example, you first need to enable the ADC, and you need to also select the prescaler for the divide. So for example, if you're selecting all ones in this bit, the lower 3 bits of the ADCSR register, you are saying that divide the source clock by 128 and then provide the resultant frequency as input to the ADC component. And you can set rest of the bits to 0 in initialization, right? So this was just initialization. After initialization, what you need to do is that you will need to read a digital value that will be converted from analog signal. So how you can read the digital value? So for that, in the ADCSR register, you first need to set the ADSC to 1. So where you are saying, okay, now start the conversion. Okay. And after signaling your hardware to start the conversion, you will need to in a loop, you will need to read the ADCSC. No. Yeah, this is wrong again. So here you will need to read ADI flag until it reads 1. So after signaling that, okay, start the conversion, you will need to repeatedly monitor the ADIF flag until it reads 1. So if it reads 1, then you will say, okay, you will understand that, okay, conversion is completed. Otherwise, you will continuously monitoring the input. Remember, we are here in this case, we are not using the interrupts to act when conversion is completed, right? So we are not using interrupts. Why? Because we had not yet covered interrupts, right? So I don't want to use the interrupt variant or interrupt mode of the ADC in this lecture at least. So once you see that, okay, ADIF flag is set equal to 1, after that you need to read the result, which is like 10-bit conversion of the analog value. So for that you need to read ADCH and ADCL, but remember that you must first read the value from ADCL and then read the byte from the ADCH. You can, if you do it not in this order, then you will end up reading the wrong value. Okay. Any questions? So that is the like structure of a program which in which you are trying to use the trying to uh, read the value converted from analog form into digital form. Okay. Uh, if no questions, then let's go to our next poll. Poll number 7. Okay, and you have 30 seconds to complete this one. Okay, so as most of you have answered, all of you have answered correctly. So you cannot read it any order. You must first read ADC low and then ADC high. Okay, now this is an example which we are actually going to also do in the lab. And that is also a reason why I have intentionally delayed the lab. I have not released the lab yet because I wanted to cover the material in the lecture and then release the lab. So hopefully I will be able to release it before your lab time. So you have lab this week, okay? Today and on Thursday, okay? So here is the example. Uh, you need to read analog input from potentiometer. Potentiometer is actually nothing but it is a source. It is a small device using which you can give the variable. You can provide variable voltage input to your microcontroller. Uh, you need to connect the potentiometer with ADC 0, right, and display the digital output on 10 LEDs, right? You need to connect those 10 LEDs on port D, low byte. So like bit 0 to bit 7 should be connected to the port D, should appear on the LEDs which are connected with the port D, and bit 8 and 9 should appear on the 2 bits on the LEDs which are connected with the 2 lines of the port B, right? And the ADC output is right adjusted, okay? So this is how like the figure looks like. So you have this potentiometer here which is connected with ADC 0. So actually it gives you variable voltage. In the lab description I will explain it how it works, right? And then you don't need to worry about, at least at this point, AV reference voltage. Uh, so you don't need to make these connections because all these connections are already made for you on your Arduino Uno board. Okay, so you don't need to worry. The important thing is that you just need to connect 10 LEDs, 8 of them with the port D and 2 with the port B. Okay. Uh, in this example, not in lab, in this example, you are going to use the internal reference voltage of 1.1. You need to set the ADC prescaler to 1/20 128, and you need to use the polling mode to detect the completion of the conversion, not interruption mode or interrupt mode. Okay. So here is the program. So first we are simply equating ADSC to 6, which is uh, the address of the bit index. So what is ADSC? This is start conversion. So this is bit number 6 in our ADCSRA register. And ADIF, this is bit number 4, bit at index 4 in ADCSRA register. So I'm just doing these equate directives because I don't want to use this number 6 and 4, so to make my program more readable. So first you need to make port B and port C an output. That is straightforward. You have done it so many times. So you simply put 0xFF in R16 and then write R16 to DDRB and DDRC, right? Uh, oh, is there a mismatch between my program and my requirement? So you need to on port B and D. Ah, yeah, there is mistake. So let me just simply correct it. Okay. Actually, we are left with only 2 minutes, so I think it's not a good idea to go over the program at this point. So let's stop here and we can do this example in next lecture, but our lab will be like closely related to this example, this lab, today's lab. So, and uh, yeah, so you have covered all the you have seen all the knowledge and information which you need to complete the lab in this lecture, and we can then continue in the next lecture from the same point. Okay, any questions? No. Okay, if no question, then that's all for now, and again have lab today. Okay, thank